Metallurgy. We're going to talk about impact strength. Guerrier Pace PE CWI. Learning objectives. We're going to talk about impact strength, which is also notch toughness. We're going to talk about how, for the most part, that really is centered on body centered cubic materials like steels and irons. We're going to talk about Charpy impact testing, and we're going to talk about the ductile to brittle transition temperature. Like I said, we're going to talk of all the mechanical properties, we're going to talk about notch toughness on this one. We've covered most of the other ones that we really needed to touch base on, but we're going to talk about notch toughness on this one. And we're going to focus on notch toughness. So toughness, we all know about toughness. Think of it in the terms of a hammer hitting an anvil. It's the ability of a material to absorb energy without breaking. A hammer striking an anvil. These two materials, the material, pretty much the same materials, but these two items can beat on each other for a long period of time and not shatter. So it's this ability to absorb energy without breaking that defines the material property known as toughness. Toughness is the opposite of brittleness. Glass is not very tough. It is brittle. An anvil is very tough. It can take a lot of punishment. So these are the opposite ends of the spectrum. The manner in which the energy is dissipated is different mechanisms for tough and brittle materials. What is toughness? Well, toughness is a combination of strength and medium ductility. So we want something that's got a high strength and a medium ductility. We don't want something that's too gummy and got high ductility, like copper. Copper's got a certain amount of toughness, but copper doesn't have that high tensile strength. So there's kind of a sweet spot we're talking about here with ductility and strength when we're talking about toughness. So this is the ability of a material to take a beating and resist fracture. Um, and it also is the ability for it to not fail once the damage is done. So where would you want a tough material? Well, hammerheads, heavy equipment like bulldozers and big shovels and haul trucks, anything where there's going to be impact over and over and over and over. This is where you want a material with good toughness. A hammer, it's going to take a beating, and slowly or suddenly applied forces are not going to affect this. It's just a material that has the ability to take a beating and not deform and not fail. That's what we're talking about with toughness. And it's once the permanent distortion starts, it's still going to take some shock or be able to absorb energy. Think of hammers. Think of a wedge you use to split wood with. Think of haul trucks, big mining equipment, things like this that can just take a beating, and even after they've started to fail, they're not going to fail immediately. That's what we're talking about when we talk about toughness. One of the things that we need to understand when we're talking about body-centered cubic materials, such as irons and steels, is they go through what's called a ductile to brittle transition zone, transition temperature. So we have a curve here that shows that at temperatures above freezing, steels are ductile materials. They can take a lot of punishment. And we see that up in the upper left-hand corner. We got the little graphic with the hammer beating on a material and it's not shattering. And the sun is shining and it's warm. Well, that's telling us that steels that would be perfectly good down here in where I'm out of in Houston, Texas, we send the same steel up to Edmonton, Alberta, and it gets up there or up into the tar sands even further north than that, and that material is going to become brittle. So we have to take special precautions for some of for materials that we're going to use in cold climates, and we're going to have to put alloying elements in them to move this curve to the left so that these materials don't shatter. But it should be noted, like I said, that this is for body-centered cubic materials. This ductile to brittle transition temperature is only for body-centered cubic materials. This doesn't count for things like aluminum or face-centered cubic materials like stainless steels. This is for body-centered cubic materials. Well, now that we've switched the game and you can see we've got our little snowman there and everything's cold, at temperatures below freezing, steels go through this ductile to brittle transition temperature, and then they lose their ability to absorb punishment. So you can see that our little Frosty the Snowman and the broken wine glass, these steels get brittle. This is because body-centered cubic materials go through a ductile to brittle transition temperature, and as we end up with brittle fractures as opposed to ductile fractures. So temperature once again plays a role in this. So the testing we do for this is called a Charpy test. So we'll take a we'll do a weld sample, or we don't have to do a weld sample, but for a material we'll cut out these little test coupons, these little Charpy test samples, and we'll put them in the machine here. And this is a hammer, and it swings down, it impacts the little part, and the little part goes flying across the room to be collected later, and then we'll figure out how much kinetic energy was absorbed by that part. And that'll tell us if it was a ductile or a brittle failure. And it'll tell us how much impact energy that particular material will take to fail. So this is what a Charpy impact test looks like. It's going to tell you how much kinetic energy was absorbed by your little test specimen. And we usually do these in tests of 3 or 6. We do multiple tests because there tends to be some scatter involved with these types of tests. So we want a good number in case there's a statistical outlier involved in one of the tests. But a lot of times for bridges or components headed somewhere north where there's a cold temperature, we're going to do Charpy impact testing. This is what a Charpy V-notch test looks like. It's just a little sample. We'll get into the sizes of it, but you know, it's only a couple inches long, and I think they're 10 millimeters by 10 millimeters wide. And they machine this little notch in there so that that it'll break, and it'll break in that spot as opposed to some other configuration of breakage and failure. But this is a Charpy V-notch test, and this is what we're talking about. Usually we're going to put these into a solution or a liquid at a certain temperature. So if it's at -20, they'll put it in alcohol with some dry ice in there and get it cooled down to -20 or whatever the temperature needs to be. Okay, so this is our second slide. We're going to talk about the Charpy V-notch test. It employs a square bar. It's 55 millimeters by 10 millimeters by 10 millimeters with a 2 millimeter deep notch on one side. The test apparatus, it swings. It's a pendulum. It's a hammer. You put it at a certain height, you let it go, and at the bottom of the swing, it whacks that little square bar, and that square bar is going to absorb kinetic energy. It's going to fracture. You're going to absorb energy. It slows it down. And then the pendulum doesn't swing up nearly as high as when you started it. And then you measure, there's a measurement there. Generally on this scale, it's going to tell you how much energy was absorbed by the little square bar. It's a calibrated scale. It's going to tell you how much energy was absorbed. Low alloy steels, as I've said, which are body-centered cubic materials, they exhibit the ductile to brittle transition. And as it gets colder, they're going to absorb a heck of a lot less kinetic energy. They're going to fail in a brittle manner. These tests are usually performed in triplicate because of the scatter in the test results. Once again, this is what notch bar test looks like. Charpy's the most common. I think there's another one called the Izod. I've never encountered it, but this is what a Charpy looks like. It's the most used. Uh, Measures resistance to sudden impact. We're talking notch toughness. That's what you're talking about at a specific temperature. Minus 20, minus 40, maybe it's 32, maybe it's 0, maybe it's 10 above. Whatever the design criteria is called out, that's the impact toughness that you're going to need. The results are used for comparisons. Like I said, you usually plus 20, 0, minus 20, minus 40. I've seen them down to like minus 200 or some number way down there but it was for a cryogenic situation, liquid natural gasification project over in Saudi or offshore somewhere. But if it's a cryogenic situation, it'll go colder. And you might end up doing it for a stainless steel or aluminum too. But most of the ones I've been involved with have been for body-centered cubic. Okay, so this is what the V-notch transition temperature curve looks like. You can see it's like a little S curve here, a little ski slope. The far right is the materials that are going to take more impact energy, and then the far left you can see is greatly diminished when you get below 100 degrees below zero Fahrenheit. It's going to be greatly reduced impact strength for those materials. So why do we care about this? Well, like I said, for engineering design, a lot of times we look at the strength first, and then we'll look at corrosion or whatever. But depending on where we're at, you might look at fatigue strength, creep strength. But for instances on, let's say, bridges or heavy equipment, something where we're going to use it in a cold climate, generally we're going to end up needing impact strengths. And if we're welding it, a lot of times weld material will not have the same, what am I trying to say? The same impact strength as would the parent material. So we need to test this to make sure that the welds aren't going to be a point of failure in regards to toughness in a colder climate. So that's why we care about this, and that's why this is important. We talked about impact strength, notch toughness. We touched base a little bit on the body-centered cubic and its relationship to impact testing. We talked about Charpy impact testing, and we talked about the ductile to brittle transition temperature. Got any questions, give me a shout. Gary Pace, PE, CWI, Katy, Texas. You can find me at texasweldingengineering.com, gpacex@gmail.com. You got any questions, shoot them my direction. I'm pretty good about answering questions. Thanks.